Okay, chapter 5. Last week we talked about the chemical bond, and we started off focusing on the ionic bond, where electrons were transferred completely from one atom to another. And we also were introduced to the three types of compound naming, type 1, 2, and 3. Remember which ones those are? Type 1 and 2 are metal, nonmetal. Type 3 is nonmetal, nonmetal. Well, the way the authors laid out the slide set, they took the type 3 and put it in this chapter. And I put them all together in the one chapter because I thought it was more stream of consciousness to go 1, 2, and 3 together. So when we get to that point in here where they're going to say, this is how you name nonmetal nonmetals, we're going to kind of skip over that because we've already covered it. Unless there's something relevant to talk about. All right, we got a lot of ground to cover, shown by the outline. This is pretty much a reminder of the key differences between the ionic and the covalent bond are that ionic bonds, first of all, they're between metals and nonmetals. And covalent bonds are always between two nonmetals. And the reason for that is that with a metal nonmetal, you get an uneven pull on electrons. Metals want to give up their electrons so they can look like a noble gas. Nonmetals want to gain electrons so they can look like a noble gas. In order to do that, with the strength of their attraction, we call that electronegativity. The strength of the electronegativity on the right-hand side of the chart is much, much higher than it is on the left-hand side. So nonmetals will draw electrons to themselves, and if you've got a metal-nonmetal interacting, those electrons are going to be transferred, and you're going to create complete ions. Either with metals, it'll be a +1, +2, +3, +4. You can go higher than that, but we're not going to experience it. And then with nonmetals, you'll go a minus, -1, -2, -3, -4. Another characteristic of ionic compounds that are different from covalent is that ionic compounds do not form discrete molecules. Right? Remember this? We have these two ions together. That's not an independent actor. It's part of an ionic matrix where you have the positives surrounded by negatives and the negatives surrounded by positives. Whereas with covalent compounds, you have discrete actors like the water molecule. Ionic compounds are solids at room temperature, except for one. Excuse me. Ionic solids are solids at room temperature. I'm thinking of elements. Right? Which element am I thinking about? That's liquid at room temperature. No idea? Mercury. Right? Remember when you filled out the extra credit? Right? Mercury, and the other liquid is a nonmetal, bromine. Okay, but now we're talking about compounds. So all ionic compounds are solids at room temperature, whereas covalent compounds can be any one of those phases, solid, liquids, or gas. When ionic solids go into solution, aqueous solution, all of them don't do that. Some of them don't go into solution, but an ionic solid that does go into solution, like sodium chloride, will dissociate into separate ions. And because it does that, that solution will now conduct electricity. So those compounds are known as electrolytes because they will allow an aqueous solution to conduct electricity. Whereas covalent compounds, not always, but usually produce non-conducting aqueous solutions. There are some exceptions. Many of the acids will produce conductive solutions. Okay, the covalent bond is a sharing of electrons. And it occurs between two nonmetals because there's not enough pull from either side to extract the electrons from one to the other. So what they have to do is share electrons when the bonds form. There's the simplest example is two hydrogen atoms. They form a bond by sharing a single electron from each side. So if we use the Lewis dot structure, which we learned last week, right, the electron's not going to be transferred to the other side, so we share them and form a bond. And we usually write it this way if we're going to show the bond. If we're not going to show the bond, we just write it this way. And a single line between two atoms is always two electrons. That's required for a bond. Now, this hydrogen now has the electronic structure of what element? It's isoelectronic with helium, with two protons and two electrons. Right, it's neutral now. But this hydrogen thinks it has two electrons in that bond. So it makes it happy, so to speak. All right, we covered that already. So when we draw these Lewis dot structures, remember they always contain only the valence electrons, those that are available for bonding. All right, so if we had the next example there is if we had hydrogen here and it encounters fluorine, then we draw the dot structure for fluorine. How many valence electrons does it have? Well, what's the Roman numeral over the halogens? It's a 7, isn't it? So that means it has 7 valence electrons. Okay, and to form a bond with hydrogen, it just needs to share one electron from either side. And that'll give you a single bond with hydrogen and fluorine. It's a covalent bond. These are called bonding electrons right here. All of these together are valence electrons. And the ones that are not part of the bonding, these right here, here, like that, those are non-bonding electrons. All right. Anytime you have two electrons, you have a bond. Sometimes you can form more than one bond between two atoms. In the case of this one and two hydrogen atoms, you have a single bond, only two electrons. In the case of carbon dioxide, if we start off with carbon, right, it has 4 valence electrons, right? It's in the 4th group over. And oxygen is one of the chalcogens. Well, it's the top of the chalcogens, has 6 electrons. So it has 1, 2, 3, 4, 5, 6. 1, 2, 3. Let's do this one. That. There. There. So how many electrons does carbon need to complete its octet? It needs 4, right? How many does oxygen need? It only needs 2. So oxygen and carbon are going to share, form a bond there, form a bond there. So now oxygen thinks it has 2 more electrons. Carbon thinks it has 2 more. Well, it still needs two more. So it gets two more from sharing with this oxygen. Okay. So now carbon has its octet, oxygen has its octet, and we write it this way. Oops, oxygen, oxygen. And then if we put in the non-bonding electrons, here, here, and here, 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 here. Now that's the Lewis structure for carbon dioxide. That one doesn't have all the electrons around it. We're showing, they're just trying to emphasize the double bonds. So between this carbon and that oxygen, we have a double bond. Right? So how many electrons? 4. 2 each. And 2 each on this side. All right. So you probably know where this is going. You can also have triple bonds. We have 2 nitrogen atoms. Where are their valence electrons? Well, nitrogen's in the 5th group, so it's got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That means this nitrogen needs 3 more electrons to make its octet. So does this one. So they just decide we're going to share these. Now this nitrogen thinks it has 2, 4, 6, 8. This one thinks it has 2, 4, 6, 8. Okay, and it has a triple bond. There's a bond, there's a bond, there's a bond. 3 bonds. And then we have non-bonding electrons here. Okay, nitrogen, this bond is extremely strong. So the air that you breathe, nitrogen may as well be an inert gas as far as our bodies are concerned. Nitrogen comes in and does physical things, like it dissolves in our tissues at these pressures. So if you're a diver, right, and you're breathing air, you go down to depth and the pressure is increasing, driving more and more nitrogen into your tissues. Then if you're down 100 feet and you decide you've got to come up real quick, all that nitrogen comes bubbling out of your system and accumulates in your joints and other tissues. And if you're not taken care of really quickly, you'll die of the bends. But it doesn't do it. It doesn't affect you chemically. It's the physical aspect of nitrogen that destroys your body under those circumstances. Have you ever heard of nitrogen fertilizers? You ever seen a bag of fertilizer in a feed store? It has 3 numbers on it sometimes, right, with a dash in between. Like, or if you've got some plant food that you feed your house plants. You know, you've seen things like this one, 10, 10, 10. Seen that before? Okay. The first one is the composition of that fertilizer in nitrogen. This is percent nitrogen. But that nitrogen has to be in a form that the plant can use. Nitrogen from the air, can't use it. Right? It has to be what we call fixed. So that's where we either do it chemically, right? We take the nitrogen and we fix it ourselves in a factory and then put it in these fertilizers, or out in nature, you need microorganisms that have the enzyme systems that can break that bond and fix nitrogen with something else, usually oxygen or hydrogen. It's an extremely strong bond. How many electrons are shared in a double covalent bond? Exactly right. Okay. I'll tell you about the other 2 numbers, but we don't have time. They're plant nutrients. Okay. Atoms of non-metallic elements have a strong tendency to form a specific number of covalent bonds. So you can use this to your advantage to sort of shortcut when you're trying to decide how many bonds are going to form between 2 atoms. You know, characteristically, this particular element forms so many bonds. Like carbon tends to form 4 bonds. Oxygen tends to form 2 bonds. Nitrogen tends to form 3 bonds. And the halogens tend to form only 1 bond. So what they're saying in that second point is the number of bonds formed is equal to the number of electrons that the atom must share to obtain the octet. And we saw that in our examples of single, double, and triple bonds. They can do it in different ways. For instance, oxygen with carbon formed a double bond with a single atom, but you can also form 2 single bonds. Now, if you have oxygen here, and you have, let's see, like that, like that, like that, 2, 4, 2, 4, 6. You can form like this with hydrogen on that side and hydrogen on this side. What do you end up with? Water. Nitrogen can form 3 bonds different ways. If it forms 3 single bonds with hydrogen, you can do like that. And then you can have a hydrogen here, hydrogen here, hydrogen here. Form your 3 bonds there. And that gives you ammonia. And various mixtures of bonds that gives you 3 bonds for the nitrogen. This is probably one of the reasons that carbon is central to living systems, because it can form so many different bonds. Not the only reason, but one of the good reasons, fundamental reasons that carbon is central to life. Okay. Covalent bonds that oxygen can form is 2. Now there's a special kind of covalent bond that's kind of mysterious. It's called the coordinate covalent bond. It's definitely a covalent bond, but both of the electrons that are part of the single bond come from 1 atom. Right? So it's like an atom comes in and steals 2 electrons from the other one in order to form the bond. Now, once the bond is formed, there's no way to tell where it came from, where those electrons came from. You have to deduce that it's a coordinate covalent bond from the possible reactants when they come together. Here's an example. If we have ClOH, let's see, that polyatomic ion, right? Yeah. Let's say we had our polyatomics, we had like that, and like this, and like this, and we had like this. Right? If we just add a hydrogen to that side, now we have the first one in that reaction, HOCl. And if we want to add an oxygen to it to make this one, now that that's gone, to make this one, notice that everybody in this group has their octet, or the hydrogen, of course, it has its duet. So what incentive is there for it to form the bond? Well, that's probably a little deep for this discussion. Let's just say there is a driving force, and it's usually related to energy. In other words, if you add oxygen to this, that makes the product more stable than the reactants. But if this oxygen comes in and it's already got 6 electrons, right, it forms a bond with the 2 electrons from the chlorine. So the chlorine hasn't gained or lost anything, but oxygen has gained to make its octet. That's a coordinate covalent bond. This is the author's idea of an explanation. I don't see any advantage to it, unless you just like pretty pictures. Here's another possibility for a coordinate covalent bond. When you look at nitrous oxide, that laughing gas, if we draw the nitrogen molecule like we did before, and then we draw the Lewis dot structure for nitrous oxide, okay, we see that between here and there, we've added an oxygen by taking those two electrons and producing that molecule. So nitrous oxide is formed from a coordinate covalent bond between nitrogen and oxygen. I'm not sure how they get carbon monoxide out of this. 2, 4, 6. Let's see, let's try it. So we're going to have the end product is going to be carbon monoxide. Right? That means we have 2, 4, 6, 8, 2, 4, 6, 8. That's good. But where did it come from? Right? How do we know that's a coordinate covalent bond? That's my question to the authors. I don't have an explanation for that one. I mean, they've met their octets, so I don't see any problem. Where did they start from? Let's say if it's carbon like this, 1, 2, 3, 4, and oxygen like this, 1, 2, 3, 4, 5, 6. Then we could form a bond here. We could form a bond here. So oxygen's already got its octet with those two bonds. But carbon doesn't. So it takes these two and puts them into a bond here. That's how it does it. That's a coordinate covalent bond. Took me a minute. Now it makes sense. So a coordinate covalent bond forms when both electrons of a pair come from one atom. All right. So we learned how to write Lewis dot structures for individual elements. Now we're going to write them for compounds. So our example here is SO2. And we've got a list of instructions, right? And I'm just going to go through them, and they're there. So first of all, you have to know that the compound exists, right? It has to be verified. We know that this compound exists, SO2. Sulfur dioxide, it's a type 3 compound, right? Non-metal, so we name it 1 sulfur, 2 oxygen, sulfur dioxide. What you do is you add up all the valence electrons that are available here. So sulfur and oxygen are from the same group. They're going to have 6 each. So 3 times 6 is 18 electrons, right? Total. Should be 18 valence electrons. Then you've got to pick a central atom. And usually the central atom is the more leans toward the metallic. So it'd be to the left or below. Sulfur is below oxygen, so it's going to be in the center. And then you form a single bond between the others. Right? And then you count those electrons, 2, 4, so minus 4 is 14 electrons left. Then you put your electrons in from the outside in. So we're going to work from the outside. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right now we have 2, 4, 6, 8 on the outside. So we have 2 electrons left. And then you move in. So this is the only available options. We have 2 electrons here. Okay. Now you try to make an octet for the ones that don't have octets. So sulfur is the only one that's missing an octet. So what we can do is, let's see, 2, 4, 6. We just need to make a double bond on one side. If we move these 2 electrons into that double bond, that makes too many for oxygen. We can't do that. So what we have to do is move 2 electrons from either side. So if we take these 2 and make a double bond, now we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And that's what these steps are showing, I hope. There we go. And then we go to the next step. Let's see. There we go. We're moving into a double bond. All right. Now, notice here that I took 2 electrons from this side. Why didn't I take them from the other side? No reason. I could have. In fact, this is a valid Lewis dot structure. Everybody's got an octet, but we could also draw it this way. Just like that, right? So we're faced with the dilemma. Which one's right? They're both right. That's the problem with this method, this Lewis dot structure method, is you can have more than one valid Lewis dot structure. And I'm scratching my head. I don't want to burden you with too much information, but I think we do cover it in here, don't we? Hold on a second. Let me check. Well, no, but I think you ought to at least hear about it. When you have 2 valid Lewis dot structures and they're equivalent in every respect except for this movement of the bond, then we have to introduce a fix. And the fix is, let's move this one over here. Let's say here, here, here. The fix is, we say these 2 structures resonate. Right, so fast, back and forth. How do we know that? That there's something in between. That's the truth, is because we know the bond length. We can figure the bond length. Double bonds should be shorter because they're stronger, right? But we do know by measurements that both of those bonds are equivalent in length. They're exactly the same. So it's not this one and it's not that one. It's somewhere in between. So we say our structures resonate. Okay. Let's move on. That's not I don't think we're gonna you're gonna have to know that for an exam. I know you're probably thinking that. All right. That's a method for drawing a Lewis dot structure for a molecule. We've already done Lewis dot structures for these. They're really simple, right? These are a little more complex, so we're going to spend time on these. How about ammonia? Okay, ammonia is a real molecule. Nitrogen has 5 valence electrons. Hydrogen has 3 times 1, right? So 3 plus 5 equals 8 electrons. Now we need to say which one's in the middle. Well, hydrogen's nearly always on the outside because it only has the opportunity to make 1 bond. So we can't put it in the middle. It just wouldn't work. So this is a no-brainer. Nitrogen goes in the middle. Then we form a bond, 1 bond each for the hydrogens. And that satisfies that 3 bond thing for nitrogen. And then we have 2, 4, 6. We have 2 electrons left over. They go right here. Okay, so that's the Lewis dot structure for ammonia. Carbon dioxide, we did that one already. And that was constructed by the same technique. carbon tetrachloride. Right? We know that exists. In fact, it was the mainstay of the dry cleaning industry for years. When you sent your fine linens to get them dry cleaned, or your dad's wool suit or whatever the case may be, they used carbon tetrachloride to clean it. Right? They put it in a big stainless steel drum. Instead of squirting water in there with soap, they squirted carbon tetrachloride in there. And it dissolved the oils and and lifted out the dirt and then flushed it away. And then all they had to do was well, initially they just let it sit and the carbon tetrachloride evaporated. That was a pollution problem. So the next step was to recover the carbon tetrachloride. In fact, they had mechanisms and machinery that would do that. And then the OSHA and EPA got involved. And they said, you can't use that anymore. We've got too many reports of cancers that are developing in dry cleaning coworkers. Right? And it was traced to this compound. So I had to get rid of it and use something else that was less hazardous. Okay, structure. So carbon is in the fourth group. It has 4 electrons. Chlorine is a halogen. It has 7 each, right? 7 times 4 is 28. So that's 32 electrons. All right. Carbon goes in the middle. All right. It's far to the left of chlorine. So carbon goes in the middle, and then we form a single bond each with chlorine. All right. You need to learn how to do this because this is the next step on our way to geometry of molecule structures, how they are oriented in 3-dimensional space. That's 2, 4, 6, 8. All right, 24 electrons left. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Octet, 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 octet. All used up. That's it. That's the Lewis dot structure for carbon tetrachloride. All right. What's the total number of dots in the Lewis structure for SO2? I should have left it up there now. If I can remember what, let's see, we had sulfur in the middle. We had one possibility was that one and that one. And we had 2 here, there, that, there. All right. Now, what do they mean by dots? Well, sometimes we put dots in here for these two. So if say 2, 4, 6, 8, 10, 12, 14, 16, 18. That may be the answer they're looking for. Yeah, that's it. So they're counting these as 2 dots, 2, 4, 6 there. They're counting both bonding and non-bonding electrons in that question. When I ask a question on test, it won't be that cryptic. Be very specific. Unambiguous. Ionic compounds containing polyatomic ions. Now, why we put those here is because polyatomic ions are covalently bound groups of atoms that happen to have a charge. And that's what that says. So when we write the structure for an ionic compound with a covalent, with a polyatomic ion, we have to write it in such a way that we put a charge on the covalent group and the other ions have their charges also. So the correct structure for potassium sulfate has the potassiums with their positive charge and the sulfate with its 2- charge. The one on the right would be incorrect. because this is not a covalent compound. It has covalent participants. So how many valence electrons are present in the polyatomic ion SO4 2 minus? SO4 2 minus. This is an important question. Sulfur and oxygen are both chalcogens, so they have 6 electrons each. So 5 times 6 is 30, right? 30 for those, but it's got 2 extra electrons. So we have to add those in. So the total is 32 electrons. Okay? And when you write it in a Lewis structure, you have to put brackets around it and give it the charge. That's what sulfate would look like in a Lewis structure. So if you wrote just the inner part with the sulfur and the 4 oxygens, and you said that's the Lewis structure, it's wrong. Because that's not all the electrons that are there. Well, that's all the electrons that are there, but there's an unbalanced charge. So you have to include the charge also. Okay, I mentioned geometry. We're almost there. Why do we need to know the geometry of a molecule? Because it has a definite bearing upon the physical and chemical properties of a substance. Think polarity. If bonds can have polarity, right? I think we mentioned that earlier. If you have, say, hydrogen and fluorine, fluorine has a stronger pull on electrons. So it won't be a complete charge transfer, but while bonded to hydrogen, you have a slightly negative character that direction and a slightly positive character this direction. That's what that little delta means, only slight, not a full charge, it's a slight charge. So it has a slight negative charge that way and slight positive charge this way. That makes the bond and the molecule in this case polar. It has a negative side and a positive side. That affects the way it behaves in pure amount. I mean, if it's pure hydrogen fluoride, they orient themselves so that we have like that, and then there's an attraction there between these two positive, negative, right? Or if it's in solution, say in aqueous solution, we have something like this, right, with its negative side and the positive side here. Well, water has its negative side, wrong way, sorry, has its positive side here, right, and its negative side here. And that's why hydrogen fluoride is very soluble in water, because it's attracted to water with that polarity. All right, the way we're going to determine structure of groups of covalently bound atoms is by this theory. It's actually a model, VSEPR. This means valence shell, electron pair, repulsion. Okay, so we're looking at valence electrons in the shell of the atom, and we're actually concerned more about, well, we can use unbonded pairs and bonded pairs, and we're interested in how they repel one another. Because in order for the molecule to be stable, those electrons are repelling each other. We need to get them as far apart from each other as possible. So the geometry allows us to predict that. We want to minimize the repulsions. Okay. We're also going to, when we say electron pair, when we start talking about counting up the pairs of electrons around a central atom, we're going to lump groups together as pairs. So what I'm saying is, if we have, say, ammonia with these hydrogens, right? We have, this is easy. There are 1, 2, 3, 4. 4 electron pairs around that central atom. But if we have something like, let me think about a good one. Like this one. Carbon dioxide. We're focused on the central atom. It has 4 pairs, but for our purposes, it only has 2 groups. So we focus on those 2 groups and set them apart from one another as far as they can go. All right. In order to apply the model, we have to draw the Lewis structure for the molecule. And we've done that. That's fairly simple. Then we count the number of groups or independent pairs. In this case, 1, 2, 3, 4. In this case, 2 around the central atom. And we're going to keep it simple. I mean, this can go, molecules can be big, and for every atom in the molecule, you can have a separate geometry. But we're going to keep it simple, right? Just one central atom possible. And we count the number of groups. This one we have 4 groups or 4 pairs. 4 groups of electrons. This one we have 2 groups. And then you predict the electronic geometry from the number of groups. And I'll give you that in just a second. From there, we go to the molecular geometry. So the molecular geometry is different from the electronic geometry because now we don't consider these electrons because there's no atom out there. We want the molecular geometry. So what does it look like here? All right. Let's see. I'm looking ahead. Okay. I probably should have put that. All right, we'll go with this. I'll set up the table here. All right, so we're going to have, in this first column, we're going to have number of electron groups around the central atom. And then we're going to have electronic geometry. Here. Then we're going to have molecular geometry. Okay. I think that was given out on me. Got this one. Okay. So around the central atom, we can have well, if the one atom is only bound to another atom, that kind of defeats the purpose because there's only one group. So if you have one group, the only possibility is linear, right? Linear between the 2 atoms. And obviously, if there are 2 atoms, then you're going to have linear here. That's probably why they don't put it in there because it's kind of ridiculous. But if you have 2 electron groups around the atom, and our example there is carbon dioxide. Then you have a linear electronic geometry. Yes, linear. I left out angles. Angles. So what's the angle between here and here, right? With this as your apex, right there, 180 degrees. Okay, and this is also going to be linear. Another example they've given there is hydrogen cyanide. But it's still got two groups. Hydrogen cyanide has, hydrogen cyanide has triple bond with this nitrogen, a single bond with this hydrogen. But it's the same situation as far as the geometry is concerned. If we have three electronic groups, and the example here is, let's see, what is that? Oh, formaldehyde. Yeah, formaldehyde. We have an oxygen here and two hydrogens there. We have 1, 2, 3 groups. And this is trigonal planar electronic geometry. And if you have 3 atoms in there and no lone pairs, then the molecular geometry is also trigonal planar. What's the angle? What's this angle here? Well, you go 360, right? So divide it into thirds. 120 degrees is the angle, the bond angle. Let's see. This is the angle for the groups. And since the molecular geometry is the same, it's also going to be 120 degrees. This would be 180 degrees. But what if we have something like, their example is this sulfur dioxide. I like water better. So if we have water, no, that's not right. Sorry. They picked that one for a good reason. So if we have sulfur dioxide, we have a lone pair here, and then we have a double bond to this oxygen and a single bond to that oxygen. We have 1, 2, 3 groups. So again, it's trigonal planar here. And the bond angle should be over here, would be 120 degrees. But if we're looking at the molecular geometry, that's simply a bent molecule. It's an angular molecule, or bent. I like bent. And it's still 120 degrees is the bond angle. Okay, so that was for 3. If we have 4 lone pairs, that should be on the next one. If we have 4 lone pairs, then our geometry, for example, is methane, right? You have 4 hydrogens here. You have 1, 2, 3, 4 groups. The most efficient geometry of this molecule is tetrahedral, triangular base pyramid. Right? And since there are no lone pairs in there, tetrahedral is also the molecular geometry. So what's the angle? Well, the angle in a tetrahedron you just have to memorize. It's 109. Yep, that was given out too. (109.5 degrees). So what we're talking about is the angle between, with the carbon as apex, go from this hydrogen to that carbon to that hydrogen. That bond angle is 109.5 degrees. And for this molecule, it would be the same because there are no lone pairs. If there's a lone pair in there, for instance, ammonia, right? If we have ammonia here like that, there, then the electronic geometry is tetrahedral. But if we cover this one up, where are those other hydrogens? Well, if we look at it in terms of a tetrahedron, nitrogen's in the middle. You got the lone pair up here. You got a hydrogen in the back, hydrogen out here, hydrogen out here. And you form the triangular base there. All right, so the tetrahedron then shape is like that. Then the bond angle here is between this nitrogen, hydrogen, nitrogen, hydrogen. There. Well, what does it look like if we cover that one up? Right? It looks like a trigonal pyramid. Yeah. It's not a perfect tetrahedron because only that's a tetrahedron. This is a trigonal pyramid. So if you got one lone pair, it's a trigonal pyramid. For water, you have oxygen and you have a lone pair here, a lone pair there, and then two hydrogens. So its electronic geometry is tetrahedral, but if we cover these two up, now we've got a bent molecule again. Okay. And the trigonal, this bond angle is going to be less than 109.5. And here's why. Because in this tetrahedron, if the electrons are not confined by a bond, then they tend to balloon. They just balloon out like that. And they put pressure on these. So that decreases the bond. It's less than 109.5. And similarly with water, which has two lone pairs up here, they balloon even further. And they squeeze the bond down to much less than 109.5. But 109.5 is our starting point. Okay, that's four lone pairs. All right, what they're making, the point that's being made here is that for more complex molecules, you can have more than one central atom. Our example here is acetylene is first. Each of those carbons is bound to two other groups. If you just focus on the one carbon on the left, right, then on either side of it is just one group. So it's linear. If you look at the other carbon, same thing. So both of those are linear. So that molecule is like this. It's just straight. If you look at hydrogen peroxide, then each side of that oxygen has four groups like water. And the bond around it is bent like this. So it's bent here on that oxygen, and it's bent here on the other oxygen. So both of those oxygens as central atoms are participating in a bent angular arrangement. Azide, hydrogen azide, you got two possibilities there. The nitrogen on the left has three groups. Right, so it's going to be trigonal planar electronic or bent angular. And then the other one has two groups around the nitrogen, which makes it linear. Right, so molecules can have multiple centers of geometry. Oh, there we go. All right, we got down to four tetrahedral. Now I'm going to have to erase some stuff to get to the next ones. All right, let's see. I'm going to have to go down maybe this far. So we have four groups around the central atom. What if we have five groups? Five groups around the central atom. In that case, it would look something like this. We would have a central atom here, and then we would have a triangle around the center, and then something up here, right? And something down here. So that would give us 1, 2, 3, 4, 5 groups. So what's that? That's called a trigonal bipyramid. Oops. Got my bipyramid. Examples. Doesn't have an example. Let's see. 5 groups. Phosphorus pentachloride. So if we have phosphorus pentachloride, then the question is, what's its electronic structure? Well, I guess I painted myself into a corner. 5 times 7 is 35, and phosphorus is 5, so it's 40 electrons. So we have P, 1, 2, 3, 4, 5, chloride, 2, 4, 6, 8, 10. So down to 30, we have 2, 4, 6. 6 times 5 is 30. So that would use them all up if we put the electrons around there. Okay. That means that we've used up all the electrons and we have no lone pairs. So this would be an example of the trigonal bipyramid electronic structure is also trigonal bipyramid molecular geometry. BCl5. All right. These expo markers are hideous. Impossible to erase, especially if the board is old. It's got lots of pits in it. Sorry. Shouldn't have done that. Okay. What if there's one missing? Let's see if we got examples. That would help. Let's see. Now that's the, okay, trigonal bipyramid on the right-hand side. We've already done the tetrahedrals and what happens if you have lone pairs in those. But on the right, we have a trigonal bipyramid. If we're missing an atom in this arrangement, that's a Y, that's a Y. If we're missing one here, we've got one in the back there. If we're missing one here, that's where the lone pair goes. It doesn't go up here, it doesn't go up there. And this has been verified. This has been verified by experiment. That lone pair goes on the triangle in the middle. So if you turn it on its side, you find that you got a bond here and a bond here, and then these two guys straight out here. It looks like this. Looks like a seesaw. So if you're missing one, you get a seesaw. If you're missing two, the second one is also on this triangle. In that case, you get a T. Now you've only got 3 atoms bound to the central one, right? 1, 2, 3. And they look like a T, T-shaped. And then if you've got a third one missing, it's also on the triangle. Now your molecule is linear. This is a lot to take in at once, isn't it? I sympathize. Yeah, let's go ahead and erase that. Well, I might go back. It's a little fainter. I think I'm going to go back to this atom because it's easier to erase. Okay, determine the shape of each of the following molecules and mention their bond angles. All right, hydrogen cyanide. All right, we've got 1 electron here, 4 there, and nitrogen is 5. And so that's 10 electrons. Carbon's in the middle. Okay, so that's 4. Minus 4 is 6. So we have 2, 4, 6. There we go. Now we've got to make an octet. We can't do it from this side because hydrogen, it's already got its duet. So we have to come from this side. We're going to take these two and these two, make a triple bond. That gives 2, 4, 6, 8, 2, 4, 6, 8. Around the central atom, we have 2 groups. That's linear. And the bond angle is 180 degrees. Okay, well, there are all the answers together. We did ammonia already. Trigonal pyramid. Why is it a trigonal pyramid? Because the electronic structure is like this. So the hydrogen back here, one out here, one out here, right? Form that like that. Cover that up, you have a trigonal pyramid. We start off at 109.5, but this lone pair balloons out and puts pressure on these other electrons in the bonds and squeezes the angle to 107 degrees. Ozone, we haven't done ozone. Right, oxygen's got 6 each, so that's 18 electrons. All right, so we have, take your pick, 3 oxygens. All right, so that's 4, 14 electrons. Now we have 14 electrons, 2, 4, 6, 8, 10, 12. All right, so now we have 2 electrons left. Put them right here. Octet, octet, we got to make an octet here. So let's move those 2 over here like that. Notice we could have done it from the other side just as well. But what do we have? We have 1, 2, 3. That's trigonal planar for electronic geometry. Trigonal planar, if we cover up that lone pair, now we have a bent molecule. Right? We would expect 120 degrees, but it's probably a little less than that because of that lone pair. That's ozone. All right. I mentioned this characteristic of elements before, electronegativity. It's simply the ability of an atom in a molecule to attract shared electrons to itself. And it's measured, actually it's measured in molecules. It's not measured independently. We assign values to each atom based upon their associations with others. And it's a complex equation to do it. And it was the most commonly used one is the Pauling scale. In the periodic table, we find that let's see, I can draw a general table like this. Let's go up. 1, 2, 3, 4, 5, 6, like that. Over here, like that, like that. We got a group there. We got 6 groups here. And transition metals here. I'm not going to draw the bottom one. The trend, particularly with the representative elements, this group and this group, the trend is from left to right, increasing electronegativity, right? Stronger attraction for electrons. And from bottom to top, increasing electronegativity. So when you put those 2 together, you have lower left to upper right. Is an increasing electronegativity. And there's an example. When you get into the transition elements, it kind of roller coasters. Right? So we stick to the representative elements to give us our trends. The lowest electronegativity is the lower left-hand corner. They've only shown rubidium there, but cesium is a little bit lower than that. Fluorine is the most electronegative element in the periodic table. And we generally don't, I'm sure they've calculated it, but we generally don't include the noble gases because they don't form bonds with other elements easily anyway. So they're not practically important. Let's see. Now, there's a reason for this. Why is it an increasing electronegativity from left to right? Well, from left to right, you're in the same period, right? You're in the same, and obviously the same energy shell. You're just adding more electrons into it, but you're adding more protons too. So those electrons are at roughly the same distance from the nucleus, and we're adding more positive charge to the nucleus. So it's not being shielded. So we're increasing positive charge by adding protons. They call it nuclear charge. We're increasing the nuclear charge from left to right. That causes a pull on electrons, a stronger pull. When we go from, well, the description here is from top to bottom, it decreases. In this case, the size of the atom is increasing from top to bottom. And as you increase the size of the atom, what you have is core electrons on the inside. And even though we're adding more protons as we go down, those core electrons are shielding the nucleus. So we're effectively decreasing the nuclear charge that the outer electrons see. And then the same argument could be used in reverse as you go from bottom to top. Okay. If lithium and fluorine react, which element will have more attraction for an electron? Well, fluorine, obviously, because it's the strongest one. In a bond between fluorine and iodine, which has more attraction for electrons? That does happen, believe it or not. Two halogens can bond, fluorine and iodine. Iodine is below fluorine, so fluorine is going to have the stronger attraction. All right. Which of these has the highest electronegativity? Well, we discount the noble gases. So we're only concerned with hydrogen, oxygen, and chlorine. If we look from left to right, chlorine should have the strongest. Oh, oxygen's the strongest. Oh, chlorine's below oxygen. Yeah. Chlorine's below oxygen, so it would have a lesser pull than oxygen. Now, the concept of bond polarity is buried in this concept of electronegatiivity. The bond is polar if you have a difference between the electronegativities of the two atoms in the bond. And I showed you one earlier, hydrogen and fluorine is extremely polar toward fluorine. And we would write that, well, so I'm going to have to go back to the, maybe purple will work. How about that? Whereas we said this, negative here and positive there, another way to show it is to draw an arrow in the direction of the polarity. This is the negative side, and that's the positive side. We show that as what's called the dipole moment of the bond. This would have no polarity at all. Two hydrogens, they have equal pull on electrons. Anytime you have a diatomic element like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, any of those where you have two of the same element bound together, it's purely non-polar covalent bond. Nobody wins. Hydrogen chloride would be an example. Chlorine is more polar than hydrogen. So that would be polar toward the chlorine. And there we show you how it's written, either this way or this way, one or the other. Now we can characterize bonds based upon the difference in polarity. So if we have, let's see, did they show one here? No, they don't show it there. Hold on a second. Let's go back. Go back. Here. If we had a bond between hydrogen and fluorine, fluorine is electronegativity of 4 and hydrogen is 2.1. If you determine the difference in polarity, minus 2.1, and that's 1.9. Then you look at this chart. I'll get to it. There it is. 1.9. On that chart, it's between 1.5 and 2. Now, if it's between a metal and a nonmetal, we call it ionic. But if it's between a nonmetal, a metal and a nonmetal, or between hydrogen and a nonmetal, we call it polar covalent. If it's between 0.4 and 1.5, that can only be between two nonmetals. Or if it's less than 0.4, that can only be between two nonmetals. If it's greater than 2, it has to be between a metal and a nonmetal. And those values are differences between the two atoms. You can determine the polarity of the bond. And this is rough, right? It's a scale to help understand the polarity of the bonds. So how about, let's see, am I going to run out of time? Probably. So this goes till, where is it? 10:50. And how many slides have I covered? Oh, not doing too bad. Okay, so let's try to put these in order, descending order of polarity of the bonds. So we look at the separation between the two atoms. Nitrogen and fluorine, they're pretty close together. Oxygen and fluorine closer. Carbon and fluorine is further apart. So in descending order of polarity, the least polar would be between oxygen and fluorine because they're the closest together. Right? They're the least polar. The most polar are the furthest apart. Right? Nitrogen and fluorine. And the one in the middle is carbon and fluorine. Right? Yeah, they're the furthest apart. So it should be wait a minute. Descending order of polarity. Most polar. Oh, I got those out of order, didn't I? Those are the furthest apart. That's in the middle, and then oxygen. Yeah, that's right. Well, the next one, see if I can do a better job of this one. Carbon and fluorine, they're really far apart. How about silicon? Silicon and fluorine are farther apart because silicon is to the left and down. So that would be the most polar. I think silicon and fluorine would be the most polar. And then carbon and fluorine. And then the last one is nitrogen and oxygen. They're right next door to each other. See if I did this one right. Okay. All right. The last one, fluorine, chlorine, they're absolutely non-polar. Okay. Boron and chlorine, they're very far apart. Sulfur and chlorine are right next to each other. So sulfur and chlorine would be here. Boron and chlorine would be like that. Boron, sulfur, chlorine, chlorine. Okay. All right, now we're going to make it a little more complicated. The question is, which of the following bonds would be the least polar, yet still be considered polar covalent? Right. So we can't have a metal and a non-metal because that's ionic. It's not even covalent. So magnesium and oxygen are out. Right, they're out. Any of the same atoms, oxygen and oxygen, that's out because we know that's not going to be polar at all. The least polar would be between carbon, oxygen, silicon oxygen, and nitrogen oxygen. Right? So the least polar would be the one that's closest to oxygen. Nitrogen is right next door to oxygen. I think it's that one. Okay. Now the question is, we've assumed that that's correct. But if we go back and look at the difference between nitrogen and oxygen, let's see if that's a correct assumption. Let's go back and look at their electronegativities. Nitrogen is 3, oxygen is 3.5, so that's 0.5 difference. You know what? Okay, just over the line. It is polar covalent by that definition. Next one, which bond would be the most polar without being considered ionic? All right, in that case, we need the furthest apart. Silicon and oxygen. Silicon and oxygen. Yeah. All right. Now that we've had a little discussion of polarity of bonds, that doesn't help us much when we're trying to decide what are the characteristics of a molecule in terms of its polarity. So we've said all this right up to this point. In order to determine the polarity of the molecule, you need two pieces of information. Are the bonds polar? Second, what's the geometry? Right? For instance, if we have carbon and oxygen in carbon dioxide, right, like that, carbon and oxygen are slightly polar. They would be polar this way for that bond and this way for that bond. But they're perfectly opposite one another, and they're polar in opposite directions. They cancel each other out. So carbon dioxide is a non-polar molecule, even though the bonds are polar. I didn't know it was going to do that. But I already gave you that one. Now for water, water's a bent molecule like that. And the polarity of the bonds toward the oxygen. But they're not symmetrical to each other, so they don't cancel. In fact, they add together. So overall, the molecule is polar in that direction. The other example they're given here is hydrogen cyanide. The hydrogen-carbon bond is polar toward carbon, and the carbon-nitrogen bond is polar toward nitrogen. They add together, even though it's linear, they add together to make it a polar molecule toward nitrogen. Okay. Draw the Lewis structure of silicon dioxide. What's silicon dioxide? Where can you find lots of silicon dioxide? You ever been to the beach? You got silicon dioxide squishing through your toes. Sand, predominantly. So draw the Lewis structure of silicon dioxide. Oops, I guess it's going to make me do it all. Silicon dioxide. All right. Silicon would be, let's see, 4. We have 4 electrons, and 2 times 6 is 12, so we have 16 electrons to play with. Silicon's in the middle. We've got an oxygen and an oxygen, so that's -4. 12 electrons, 2, 4, 6, 8, 10, 12. Okay? Oxygen's got its octet, but silicon doesn't. So we're going to take one from this side and one from that side. Make a double bond here and double bond there. Right. That has 2 groups around the silicon and no lone pairs. So the molecular geometry is linear. And even though oxygen is more electronegative this way, this way, they cancel each other out. So that molecule is non-polar. The bonds are polar, but the molecule overall is non-polar because they're symmetrical and equal in magnitude, but opposite in direction. All right. Which of the following molecules are polar? Well, difluorine can't be, right? There's no way because they're equal in electronegativity. So we can cross this one out as completely nonpolar. HF is strongly polar toward the fluorine. Ammonia is like this. We drew it before. Like that. Actually, the bonds are between this nitrogen here and that nitrogen and this hydrogen, that nitrogen, this hydrogen. Like that. So this is going to be, the bonds are going to be this direction, polar. And overall, the molecule is going to be polar in that direction. SO2. Let's see, we drew this one before, didn't we? Let's see, 3 times 6 is 18. We have sulfur, oxygen, 2 minus 4, 14, 2, 4, 6, yeah, 8, 10, 12. Yeah, we drew this one before. This one is going to be bent. Oxygen is more polar, so it's going to be this direction for oxygen, this direction for oxygen, and it's asymmetrical. Now, it's not going to be very polar, right? Even though the bonds are polar this direction, you got that lone pair on this side that's pulling the other way. So it's only very slightly polar, but by definition polar. And we drew carbon tetrachloride before, right? Carbon tetrachloride, right, is symmetrical, tetrahedral, and even though it would be, the bonds would be polar toward chlorine, they're all pointing to the points of a tetrahedron and they cancel one another out. Excuse me. So the only polar ones here are HF, ammonia, and SO2. Now, the relative polarity would be another discussion. Which of these is a polar compound? Well, we did carbon dioxide before. It's symmetrical, right? So it's nonpolar. How about beryllium chloride? Okay, beryllium Actually, beryllium's a metal. That would be an ionic compound. I wouldn't call it polar. Water's polar, definitely. Right? That one's polar. Methane is like carbon tetrachloride. It's a tetrahedron with no lone pairs. So it's non-polar. I hope they're not claiming beryllium chloride is polar. No, water. Beryllium chloride is ionic. It's not polar covalent. That was kind of a trick question, I think. All right. This is the point where we covered this in chapter 4. Binary molecular compounds are type 3 compounds. They're non-metal, non-metal. And these are the naming conventions. You already know how to do these. You just say how many there are. Like N2O4 is dinitrogen tetroxide. And there are your prefixes. The Greek prefixes from 1 through 10. And examples. Some compounds have accepted common names, and these are historical. They're inherited. So when you see H2O, it's not dihydrogen monoxide, it's water. Hydrogen peroxide is a common name for H2O2. Ammonia, hydrazine, N2H4, which is a very dangerous chemical. It was used by the Nazis in their little rocket planes. Killed a bunch of people too. I mean, mechanics on the ground working with the stuff. Methane, CH4. Methane is named, methane and ethane are named by organic conventions. Right, so just accept those for what they are. Dinitrogen monoxide is nitrous oxide, and NO is nitric oxide. That's the one that you're supposed to get from super beets. You eat super beets and it converts whatever's in there into nitric oxide, goes in your system, causes your vessels to relax and decrease your blood pressure. That's nitric oxide. Which one is named incorrectly? We did this one before, I think. The top one, nitrogen dioxide, that's true. Phosphorus pentoxide, B is wrong. It's diphosphorus pentoxide. Phosphorus trichloride is true. Sulfur trioxide is true. Iodine monochloride is true. So there's the bad one right there. Oh, good. Concept question at the end. That means we're almost over it. Right, we can, I guess it's just going to be one lab group today, which is all right. You get more hands-on with just 2 of you in a group. An unknown is thought to be an aqueous salt solution. However, it was determined not to be a conductor of electrical current. Aha, so it's not ionic. Through analysis, it's found that the unknown contains carbon, hydrogen, chlorine in a ratio of 1 to 1 to 3. Carbon, hydrogen, and chlorine in that ratio. Which one of the following represents the Lewis structure, molecular geometry, and classification of the unknown? All right. Well, let's see. First of all, do they all have the same empirical formula or molecular formula, as the case may be? Let's see. The first one is, yep, that fits. Second one fits. Third one fits. Okay, they all have the same ratios. Okay, that's good. But what we need now is the Lewis dot structure. All right, so carbon has 4, hydrogen has 1, 3 times 7 is 21. So that's 26 electrons. All right, let's build it from carbon on the inside. Okay, that's 4. 22 electrons left. Hydrogen's got all it needs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, with 4 electrons left over. Is that right? 2, 4, 6, 8. And then 3 times 6 is 18. Oh, that's it. They're all used up. Right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 26. They're all used up, just like that. Okay, which one matches that one? Well, the first two don't, because chlorine's got no electrons around it except in the bonds. So it's either C or D. Can't be C because hydrogen's got too many electrons. Hydrogen doesn't have an octet. It only goes for a duet. All right, so by process of elimination, D would have to be the right answer. And do the other fit? Tetrahedral arrangement? Yep. Covalent compound? Yep, they're all nonmetals. Okay, so D is the correct answer. All right. Oh, we got another one. Okay, let's see what we can do with this one. Let's see if I got another purple. Yeah. Maybe this will work better. A liquid molecular compound is given to you and you're told to handle it with caution. It can cause damage or death if it's consumed in large quantities, if it enters your lungs, if you're hit with a frozen chunk of this material, or if a hot solution of it is spilled on you. However, this liquid is necessary to sustain life. The liquid is pure molecular compound, all right? All nonmetals, has no taste, is known to contain hydrogen and oxygen. Identify the liquid, its molecular geometry, and whether it's polar or nonpolar. Well, I think it's fairly obvious, right? It's got to be water. You can overdose on water. Takes a lot. If you get it in your lungs, of course, you drown. If you get hit by a chunk of ice or you get flashed with steam, that can damage you. So is water linear? No, it's angular. Right? The electronic structure is tetrahedral, but it's got 2 lone pairs. Right? So you got the hydrogens down here in the bent mode. So that's angular. And is it polar? Definitely polar. Right? If water were not polar, we'd be in huge trouble. Because at these temperatures and this pressure on the Earth's surface, there would be no water. It would all be gas. Wouldn't be liquid water at all. No oceans. Just a lot of dead people. Okay.